Okay, AP Chemistry, these are the answers to the day 35, day 36. That's Monday and Tuesday gas stoichiometry. It says it's due Thursday. I'm getting these up on Thursday. So go ahead and take the weekend if you need it. But you have another assignment due over the weekend, and you'll have another one tomorrow. So try to get these done today. I'll have these up by mid-afternoon. Okay, so let's go ahead and answer these. These are stoichiometry problems, very similar to what you've seen before. And we did these, something like these in class, so I went ahead and corrected some of the errors that were in class. Okay, so what we're saying here is that watch the instructional video before you do this, and what you'll know is that at standard temperature pressure, which is 0 degrees centigrade and 1 atmosphere, that 1 mole of gas occupies 22.4 liters. So think of those 2-liter soda bottles that you see everywhere that you probably have at home. So it's 11 of those. That they would contain, if you just filled them with air, open the cap and fill them with air, you would have basically a mole of air inside those 11 bottles. That's pretty much what that's saying. Assuming that the temperature is, well, that temperature is much warmer than 0 degrees centigrade, but it is standard atmospheric pressure, so it would be a bit different than that. But anyway, so 0 degrees centigrade, 1 atmospheric pressure, you'll have 1 mole and 22.4 liters. It doesn't matter what the gas is. Notice this applies to H2 gas, O2 gas, H2O. Doesn't matter what it is. Okay, so here we go. So the question is, how many grams of H2O can be formed with 4.34 liters of H2? So it's asking for grams of H2O. So that's going to be down here in the grams row. That's something we can weigh on a scale, so that's out there in our world. And you're going to start with 4.34 liters of H2. So that's right here, 4.34. Okay, so we start here. And we end way over here. Okay. All right, so the path is, it's 3 steps. We need to get into the equation using this conversion that we just developed here. Then we get across the equation from grams of H2 to from moles of H2 to moles of H2O. Looking at that G stands for gas, okay? So moles to moles, and then you get out to where your desired answer, grams of H2O, by the molar mass conversion that we've been using for quite a while. So we'll go ahead and do this. Okay, so the first conversion is 1 mole H2O for 22.4 liters. So one of those goes on the top and one of them goes on the bottom. Which is it? Well, we need liters of H2O to cancel out. So we're going to put the 22.4 liters of H2 on the bottom. Hopefully this kind of is becoming, natural enough that you don't have to write every ratio and every conversion factor. And you have 1 mole of H2 there. Liters of H2, liters of H2. Okay, now you're going to have moles of H2 cancel out. So the next conversion is from moles of H2 to moles of H2O. It's a 2-to-2 ratio. We need moles of H2 to cancel out here, so we're going to put 2 moles of H2 right there. And on the top, we're going to put 2 H2O. Put the word mole there. Okay, so moles of H2 cancel. Now the last conversion is the molar mass conversion that we've used many times. And we have moles of H2O on the top here. We need grams of H2O to end up on the top. So we're going to go ahead and do that. 18.02 grams on the top. And 1 mole of H2O on the bottom. So moles of H2O and moles of H2O cancel. And the last thing that you have for the final unit is grams of H2. So now you multiply everything on the top, divide by everything on the bottom. 4.34 times 1 times 2 times 18.02 divided by 22.4 divided by 2 equals, and it's 13.96, and we're limited to 3 significant figures, so we're going to call that 14.0. Okay, let's move on to the next one. The next one is asking us how many liters of H2O, so up here we have liters of H2O, can be formed from 5.9 grams of O2. So we have 5.9 down here in the grams row. So our path is going to be molar mass into the equation, O2 across to H2O in moles, moles to moles, and then out using moles to liters to get the final number of liters of H2O. It did not say H2O gas, but we'll assume that that's what they're talking about here. Okay, so we want to know some number of H2O gas, and we're starting with 5.9 grams of O2. Okay, it's 1, 2, 3 conversions. You can see there. Try to get everything on screen here. So just barely. Okay, it's 3 conversions. All right. So first one is molar mass, 1 mole 32 to get us into the equation there. So we need grams of O2 to cancel out. I'm going to leave off the zeros just to save space here. So grams of O2, right there. Now we're moles of O2 to moles of H2O. We have moles of O2 on the top here, so we need it on the bottom. So we're using 1 to 2 here, 1 mole of O2 and 2 moles of H2O. Moles of O2 cancels. And now we need to get from moles of H2O to liters, so we use this conversion right here. We need moles on the bottom. And we need the 22.4 liters on the top. Okay, so let me get this on screen better here. Okay, so moles of H2O cancels moles of H2O, liters H2O is last man standing. I put grams of H2O, that was wrong. It was asking for liters, so we caught that, good for you. I'll change it now. So it's liters of H2O. Okay, so multiply everything on the top, divide by everything on the bottom. And I get 8.26, and we're limited to 2 significant figures, so we'll call it 8.3. Okay, so now we're going to do non-STP. That means we're going to have to use the ideal gas law, which is PV equals nRT. And we're going to need that to be solved for N. So that's going to be N equals PV over RT. And the R equals... Okay, so that's all the information you need to do this. So first we're going to have to figure out N. So the question is saying H2 gas is held in a 5.1 liter container at a temperature of 25 degrees C and 780 torr. How many moles of H2O gas will be produced? Okay, so we're trying to get to H2O gas. So way over here, because we're going to need some space, real space on this. And it is asking for moles. Okay, so what we're going to do is use this information to figure out how many moles of H2 gas we have, and then that'll put us right here right away. No conversions are needed except those things. And then we have to just go straight across to H2O and we'll be done because it's asking us for moles. Alright, so a few things we have to do. Pressure. write them out like this. It's 780 torr times, and you've got to know your conversions. Let's go ahead and write them out. Write them out. Write them at the top, but you're not going to be able to see them on the screen for most of the problem. You should memorize these. It's 1 atmosphere equals 760 millimeters of mercury equals 760 torr equals 101.3 kilopascals equals 101,325 pascals. Okay, so just have those written down on your own sheet of paper and write them out every time you do one of these problems, so they just become natural to you. You shouldn't even have to think about them. You should be doing these pressure conversions just automatically. Okay. You just do that by doing enough problems to where they just stick. So it's 780 torr times 1 atmosphere. Okay, this is our guide as to what units we need. For pressure, we need atmospheres. So it's 1 atmosphere for every 760 torr. Torr cancel. And you end up with 1.03 atmospheres. Okay, next we have volume. Volume equals 5.1 liters. That's good. We need to be in liters here. If it was milliliters, we'd have to make the conversion to liters. That one's fine. Okay. Next is temperature. And that's in centigrade. It has to be in Kelvin. That's what the constant is calibrated in here. So that's going to be 25 plus 273. And this is a pretty common temperature you'll see in these problems. 273. It's 298. So get used to seeing this 298. And that's Kelvin. Okay? Alright, so now we're going to plug in the numbers down here. N equals pressure. Okay, so there it is. We filled in this formula right here with everything that we have. So let's cancel our units. Atmosphere is in numerator top, and atmosphere down here is in denominator top, so they have the word top in common. They cancel. Liters here is in numerator top, and liters here is in denominator top. They both cancel. Kelvin is in denominator top and denominator bottom. They both have the word denominator in common, so they cancel. Moles is the only thing left. It's in the denominator bottom, so you're going to flip that bottom fraction. It's going to come all the way up to numerator top. And that's what N is. N is the number of moles. So what is that number going to be? It's 1.03, and I get 0.214. And we have 3 sig fig there. No, we have 2 there. So I'm going to call it 0.21. We're really not done with the problem though, so let's go ahead and write it, and then we'll do the sig fig at the end. Okay, so there's the number of moles. And that's number of moles of H2. Okay, this is what we were told, that H2 has all these parameters. So that's going to be 0.214 mole of H2 times, we only need 1 box for this one, thank goodness, because I'm running out of room. We need to get from moles of H2 to moles of moles of H2O, right there. We only need to get from that box to that box, okay? So that's 2 moles of H2O. And on the bottom, we need moles of H2O to cancel. So cancel moles of H2O, moles of H2O. So it's simply going to be 2 over 2 is just going to cancel out, right? So it's just going to be this number right here, 0.2. And we said we could only go to 2 sig fig, so it's 0.21. Moles of H2O is what you're going to end up with. It doesn't make sense. I'm going to change this. O2. Okay, so I'm going to change it from O2 gas. Okay? So I'll change that on the assignment. If you haven't, if you've already done it like this, that's fine. Go ahead and keep it. Okay, so we're going from O2 gas. So it's So we're going from O2 gas, which is up here, but that's our known. We just have to figure out how many moles it is. So really what our known is there once we do the calculation. How many grams, how many grams of water? So the bottom line is the question mark is grams of water here. And we're going to calculate how many moles using PV equals nRT. So let's go ahead and do that. Okay, so go ahead and line up your variables. It's the best way to do it. Over on the left, pressure equals 102.7 pascals, kilopascals. And you need to make a conversion to atmospheres. So 1 atmosphere for every 101.3 kilopascals. And that gives you 101. And we got 4 significant figures, so it's 101 point, no, it's 1.014. So 1.01 there. Volume. Volume is in liters already, so that's fine. Temperature. Same conversions we had to do in the last problem. Is 35 C. And that's going to equal 308 Kelvin. Okay, so that's everything. We're going to write our equation down below. I'm not going to show the graphical organizers. It's just impossible. It's way up there. So let's just reason out what we're doing. First of all, we're figuring number of moles of O2. Okay, so N, and I can put in parentheses O2 there, equals pressure. Okay, so we'll figure out the number of moles here. So atmosphere, numerator top, denominator top cancels, liters, numerator top, denominator top cancels, Kelvin, denominator top, denominator bottom cancels. Again, same way it canceled last time. So I'm going to put that actually down here. The number of moles of O2, I get 0.1444. I have 4 significant figures there, so I'm going to hold that till the end of the problem. Okay, so now where are we here? We're here. It's right there, 0.1444 moles of O2. And we need to get out here, so it's 2 conversions. Moles of O2 to moles of H2O, and then molar mass to get us out to the final answer. Let's go ahead and just write that out. Draw a line here, so draw the space, so screen. Fit my boxes in. There's 1 box. There's 2 boxes. And then what we're trying to get to is grams of H2O. Okay, so the first box, again, is going to be moles of O2 to moles of H2O. We need moles of O2 to cancel out here. Moles of O2 cancels. And now we need to get from moles of H2O out using the molar mass to get to grams. Okay, moles of H2O cancels. So 0.1444 times 2 times 18.02 divided by 1 will give us our final answer in grams of H2O. And it's 5.204. And sig fig, we're limited to 2 right there. So we're going to go with 5.2. Okay, and that's how you do that. Alright, it's just a lot of little messy arithmetic in there to figure out the number of moles if it's not an ideal gas. And that's how you do that. Okay, several pages to this assignment, so let's knock down some of these. And again, you need to see the instruction video before you try to do this. Otherwise, you just won't have any idea which one you're doing. So, which will effuse faster, Cl2 or F2, and how much faster will it effuse? So for that, you need a periodic table. So we bring in the periodic table, and we see F has a molar mass of 19 grams per mole. Cl is much heavier. It has a molar mass of 35.45, so the lighter one is going to move faster. That's just common sense, and that's the answer to that, okay? So, so F2 will effuse faster. And Graham's law of diffusion says that the relative speed, in other words, how much faster the smaller one will move than the larger one, is given by this formula. Okay, so the larger one, now I gave you the mass of a single atom, but these are actually diatomic molecules. So 2 times 19 is 38. That's the lighter one. So that's going to go on the bottom. Grams per mole. And grams per mole is going to cancel out. And 35.45 is going to be 70.90. That's going to go on the top. 2 of those. So again, grams per mole is going to cancel out. You're just going to get a number value. It's how many times faster. So divide 70.9 divided by 30. Give you 1.37, and sig fig, that's fine. So it equals 1.37. So write out what that means. I'll write it up here because I'm running out of space down here. The lighter of the 2 gases is fluorine, so fluorine will effuse 1.37 times faster than chlorine. It doesn't tell you how fast it's going. It doesn't tell you how many meters per second it's going or anything. It just tells you that it will effuse faster. I'm going to leave this one for you to do. It's exactly the same thing. You're using argon and krypton. Those are 2 noble gases, so they will not be diatomic. They will just be single atoms. Okay, what is mean free path? I want you to, it's just a definition given on the video so you can answer that. I also sometimes make references, now that we're going to get more and more into the textbook. BLB is your textbook. It's Brown LeMay Burston is the name of your textbook. So it's telling you it's in your textbook on page 420, and you can read about it there. More and more I'll give you questions where I want you to go research in your textbook, okay? Write the van der Waals equation. What is the purpose of the van der Waals equation? It's on the video, so if you want to just watch the video, you can get the answer there, or it's in your textbook on page 422. So I'll leave questions like that for you to do. Okay, I'm going to keep moving along here. CH4 has a molar mass of 16 grams per mole. It's actually 16.05. And back in the day, I used to just round things to the whole number. I don't anymore. So it's 16.05 grams per mole, 12.01 for the carbon, and 1.01 times 4 for the hydrogens. The helium gas has a molar mass of 4, and that's accurate. That's exactly off the periodic table. How many times faster will helium effuse? Okay, go ahead and do that. Okay, it's just like it's just like number 5. All right, which will effuse faster? And there was some duplicates. That was pointed out to me. Scratch that. Scratch 11. See, I'm scratching out your work here. Isn't that great? And 12. I think those 3 were duplicated. Thank you for pointing that out, Daniel. Okay, 13. That's also duplicated. Okay, 14 is straight out of the video, which is straight out of your textbook. You can get it either place. I got the 5 out of your textbook, and they're in the video. Okay, what is the kinetic molecular theory? It's basically what is the definition of a gas. That's kind of a fancy way of saying that. Well, I'm going to cut this one on next video, so I'll go ahead and get this one up online for you to get started with.